All right, well, we'll go ahead and get started. I'd like to introduce our speaker today. This is Jason Otkin. He works at the Cooperative Institute for Meteorological and Satellite Studies, or CIMSS, which is at the University of Wisconsin-Madison. He earned his master's degree there, and then he's currently working on his PhD through the University of Reading. Since he started working at CIMSS, he's had quite a diverse set of topic areas. He's had research in drought monitoring and prediction, data assimilation, and also using observed and synthetic satellite imagery for multiple purposes. Today, he's going to be talking to us about verifying the HRRR model, and this is in part funded by the DTC visitor program. So with that, I'll let you get started.
All right, thank you for the introduction. In this talk, I'm going to present results from several new studies that we're working on in which we are developing a near real-time satellite-based verification and forecaster guidance system for the high-resolution rapid refresh model that uses GOES infrared brightness temperature observations. For the system, we're using a variety of statistical measures to assess the forecast accuracy. This ranges from more traditional grid point statistics to a more complex object-based verification. But before I show you some results from these studies, I'm first want to thank my co-authors, especially Sarah Griffin, who did most of the work I'm going to be presenting today. And also want to thank the NOAA GOES-R Risk Reduction Program and the Developmental Testbed Center for providing funds that supported these efforts. Okay, so I'm going to talk about 3 different projects today, each of which use GOES infrared brightness temperatures to assess the forecast accuracy. The first part of the talk, I'm going to show some of the capabilities of a near real-time verification system that we've developed for the HRRR model. And then I'm going to discuss results from a 24-hour case study from last year that was used to assess the merits of different analysis methods for cloud verification. And then at the end of the talk, I'm going to spend some time discussing results from a longer-term seasonal analysis that was performed using object-based verification courtesy of the MODE software that was developed here at NCAR. And the primary focus of that is to look at the accuracy of the cloud field. Okay, so early last year, we began to develop a near real-time GOES-based verification system for the HRRR model that can be used by forecasters to quickly determine the accuracy of current and prior HRRR model forecasts. Now, with the availability of many overlapping forecast cycles, having objective tools that can be used to quickly assess the forecast accuracy has the potential to improve the efficiency of forecast evaluation efforts by allowing them to more quickly determine which forecast is most accurate at the current time. Now, this can be very important because the most accurate forecast may not be the most recent one. This could be because of errors in initialization, different error growth rates. So it's important to be able to quickly determine which one is most accurate. Now, with this system, the HRRR forecasts are ranked through comparison of observed and simulated brightness temperatures from the GOES sensor. And the statistics are computed separately for predefined regions across the United States. And this is done so that you can zoom in on specific regions of interest. I also want to point out that a prototype version of the system was demonstrated last year at the Hazardous Weather Testbed Spring Experiment in Norman, Oklahoma, and I'm also at the Aviation Weather Testbed in Kansas City. Okay, so I'm going to spend a few minutes now describing some of the capabilities of our real-time verification system. This slide just shows a sample screenshot of the project homepage. As I mentioned in the previous slide, you can assess the forecast accuracy for different regions across the United States. Those are the various boxes on this image. For convenience, these regions align with those that are used on the Storm Prediction Center's mesoscale analysis page. But the system is very flexible, so we can quickly recompute these statistics for other regions of interest. Now, if you click on one of the boxes in the previous slide, you'll then be taken to a web page that looks like this. Now, in the upper left, over here to the left of the domain image in the middle, is a drop-down menu where you can choose the GOES observation time that you want to use to assess the forecast accuracy. This will include the most recent time and then also the previous 6 hours, but most likely you're just going to want to focus on the current time when assessing the forecast accuracy. And then over here to the right, if you click on this box, you can switch between the GOES infrared window band and the GOES water vapor sensitive band. Today I'm just going to focus on the infrared window band. And then below this top banner, once you get down here, you can then rank the accuracy of all the forecasts available at that observation time based on their RMSE bias or mean absolute error. I can do that by clicking on the little arrows next to those statistics names. Later this year, we plan to expand this to include some other verification metrics that can account for some other things. And then finally, on the right side of each of these rows, you can then see a side-by-side comparison of the forecast and observed imagery at the current time. And then if you click on one of those images, you'll then be taken to an animation that shows the forecast imagery on the left and the observed imagery on the right for whichever forecast cycle you clicked on. These animations can be very useful because they allow forecasters, who are very used to looking at satellite imagery to assess current conditions. In this case, though, they can use it to determine, how well the forecast is matching up with observations at the current time, and then look at its evolution during the rest of the forecast. So of course with these animations, you're going to have both the observed and forecast imagery for the first few hours of the forecast, because that's how long it takes for us to get the data and process the data. But then of course you're just going to have the forecast imagery once you get beyond the current time. Okay, so then if you scroll to the bottom of the web page, you'll then see 3 error matrix graphics that look like this. These graphics show how the forecast errors have been changing with time during the previous 12 forecast cycles. They can be very useful because they allow forecasters to quickly identify trends in the forecast errors, and also to determine if any one particular forecast cycle is doing particularly well or poorly at the current time. These graphics are organized so that the most recent forecast is at the top row, the oldest is at the bottom row, and then the observation time is shown on the x-axis. It goes from the newest on the left to the oldest on the right. With this formulation, this then means that if you wanted to assess the forecast accuracy at the current time, they would just need to look at the left column and compare the forecast accuracy for each cycle in that column. Okay, so I'm going to show a couple examples on how those error matrix graphics can be used to assess the forecast accuracy. In this particular example, this one shows the bias error, shows an RMSE and bias error matrix for the Midwestern United States from the 19th of November of last year. The bias is shown in color, with the red colors indicating a positive bias and the blue colors indicating a negative bias. And then the RMSE values are overlaid on top. This region and time period was chosen because clear sky conditions were present across that whole area. And because we're looking at the window band, so this is the 10 point, yes?
So which variable are you comparing to?
Well, this is the 10.8 micron window band brightness temperatures. So because this is clear sky conditions, the window band will see all the way to the surface. So primarily what we're looking at here are errors in things like surface temperature is what we're looking at. And if you look at this graphic, if you go from right to left along each of these rows, you can see that the forecasts have a pretty similar evolution, regardless of when they are initialized. And what I mean by that is that they all have a positive bias here between about 5 UTC and 12 UTC that then transitions into a negative bias and becomes quite large by the time you get to 16 UTC. And again, because we're looking at the surface in this particular case, because it's clear skies, what we're seeing here are errors in surface temperatures. So that the surface temperatures are too warm at night and then become too cold during the day. So the diurnal cycle is less than what's being observed by the satellite observations. Yes?
So Rebecca's paper pretty well showed this as well. And I'm curious because you're saying surface temperatures, but isn't the satellite truly seeing skin temperatures?
Yes.
Okay.
Yes.
Should I let you go on then?
Yeah. Yes, technically it's skin temperature.
Well, if you're verifying with WRF or her surface temperatures, is it really?
No. We're
Is it
We're just comparing observed and forecast brightness temperatures.
Right, but
and
you have to pick something from WRF where it's clear sky to say what it's actually using.
No.
Meter temperature or skin temperature.
We're
or
using
soil temperature.
we're using skin temperature to compute these brightness temperatures, and I'm just making the inference that because this is the window band and there weren't clouds,
Yeah,
that what we're
but
seeing is the surface.
Is it really a soil temperature?
facility the tool is otherwise?
I mean, because the LSM people are responsible for the soil temperature, so, or whatever you're
Yeah.
calling it, skin temperature. I'm looking at Jimmy because I'm curious what variable you would choose to pick.
I'm assuming that before would model to compute the brightness temperature, and it would take the skin temperature as input.
Yes.
And the
My point is
atmospheric
you're
profile.
assuming. That's
Well,
my point, that's why I'm asking.
Well,
That's what we're doing.
and the
Yeah.
atmospheric profile you have to-
Okay.
Yeah.
It's a pretty big deal because, of course, you have to pick the right temperature. That's why I'm asking that.
Yeah.
Okay, thanks.
Yeah.
So, I'll just reiterate, these are errors of the model predicted skin temperature.
No, these are actually errors in the model predicted brightness temperature.
Okay.
And because this is a window band, it's an atmospheric window band, meaning that if there are clouds, it's going to see the clouds, but if there aren't clouds, it's going to see all the way to the surface. And then the main point at that part is the surface skin temperature, that and emissivity. And I'm assuming that most of this signal is surface temperature or skin temperature.
Okay, but it's not tumor
Yeah.
air temperature,
No.
which is what
No.
a lot of people immediately think of when you hear surface temperature.
Yes.
So we must-
It's always hard to know which one to say. Because a lot of people don't know what skin temperature is either, so it's just kind of it's at the surface. I mean, they're going to be strongly related, surface temperature and 2 meter temperature, but it is important which one you actually use.
So your definition is clear here for the comparison is the model is clear and the observations are clear, or only the observations clear?
Well, in this particular case, we chose it because the observations were clear, and for the most part, the model was too. Because we're not trying to match to make sure that we're both clear. I
So
mean,
the observations are clear, but the model can have clouds.
it could, but for the most part, it didn't in this case. And this is just an example. I mean, we're not using this for verification. It's more just of a demonstration of what you can see with these matrix graphics.
Jason, one more, sorry.
Sure.
Excellent piece, though, because it's telling us something about the rock LSM, in my opinion. And
Yep.
therefore, has anybody looked at, other than the rock LSM, like NOAA or NOAA MP, to see if there's an improvement on that? Because these are pretty big errors that are
Yeah.
greatly alter convective
Sure.
signal cycles.
Sure. I haven't looked at it.
Okay. I guess you have a job for Tanya.
I do. All right, so we'll see if this next one elicits as much conversation. Okay, so this one is another RMSE and bias error matrix. Now this one is from the Central Plains. This is from middle of May of this past year, or actually this year, of 2016. Now you can see, if we flip between these two graphics, they're very different. One of the reasons why they're very different is we chose this case because unlike the previous one, which was mostly clear, this one was mostly cloudy. So it had a lot of upper level clouds across this domain throughout this time period. And you can see again that each of the forecast cycles, as you move from right to left, they all follow a very similar trajectory in these errors. They all start out with a very large positive bias that then transitions into a large negative bias by the time you get to forecast hours, say like 3, 4, and 5, and then that persists throughout the rest of the forecast period. So what we're seeing in this case is, again, this is the window band. So in this case now we're seeing clouds. It's very sensitive to clouds. And by having this warm bias initially, it's telling us that the initialization in the HRRR model does not have enough clouds, does not have enough mid and upper level clouds, which means that you're going to be seeing deeper into the atmosphere where it's warmer, and thus you're going to get this warm bias. But then that's going to be rapidly replaced by there being too many upper level clouds, and that's what leads to the cold bias at these later forecast hours. And this then suggests that there's an issue with the model spin-up process, that it may be too vigorous. It's producing convection that's too strong, and in the process launches too much cloud condensate into the upper troposphere, so you end up with too many clouds, and thus this cold bias. All right, I'm going to move on then. Okay, so now I'm going to spend some time showing some results from a 24-hour case study that we used from last year. This was used to assess the merits of different analysis methods for cloud verification. So for this project then, again, we assessed the HRRR forecast accuracy using GOES infrared brightness temperatures. The primary focus was to assess the accuracy of the cloud and moisture fields, and this was done using observations from the 6.7 micron band that will be sensitive to clouds and water vapor in the middle and upper troposphere. And then this 10.7 micron window band, which will see clouds when they are present, but we'll see down on the surface when they are missing. For this talk, though, I'm just going to focus on the 10.7 micron band because we're most interested in clouds for this particular talk. So we assessed the forecast accuracy. I'm using many different statistical measures. These range from traditional grid point statistics, things like RMSE and bias, to neighborhood methods like the fraction skill score, and then also the object-based tools from MODE. And together, we would hope that the use of traditional neighborhood-based and object-based verification, they tell you different things. So they should provide a more complete analysis of the forecast accuracy than any one method can provide by itself. Okay, so we focused on a 24-hour time period from 12 UTC on July 23rd to 12 UTC on July 24th. This is from last year. We focused on 3 regions, the north-central U.S. in the red box, central in black, and then southeastern U.S. in blue. We chose this time period because of the different modes of convection across these regions. So we had a pretty widespread severe convection up here across the northern U.S., a more isolated convection in the central, and then a secondary area of widespread convection, in this case, mostly strong winds across the southeastern U.S. These were primarily associated with extratropical cyclone up here, and then the sea breeze and stationary front across the southeastern U.S. Okay, so the first thing we're going to look at here is something that we call a quilt diagram. It shows how the forecast errors, in this case the mean bias error, is changing with time throughout this 24-hour time period. Now this is organized so that the forecast hour is along the y-axis. It goes from the initialization at the bottom to 24 hours at the top. The observation time goes along the x-axis from 12 UTC on the 23rd over here to the 24th on the right. This means that if you wanted to look at the evolution of the forecast errors for any one forecast cycle, that you'd want to go along a diagonal going from the lower left up to the upper right. That'll be for any one forecast cycle. The red and the pinks are positive bias, and then the blues are negative bias. And again, this is the 10.8 micron window band that we're looking at here. So I'm going to point out a few things. The first of these is if you look at the bottom, you can again see that all the forecast cycles tend to have this positive bias, maybe up to a couple degrees. This lasts through the first 2 hours for most of the forecasts. And then this transitions into a negative bias here between forecast hours 3 and 8 for maybe about 2/3 or 3/4 of the forecast. And again, this is consistent with what we saw in a couple slides ago in that error matrix graphic. Another thing I want to point out is that if you follow some of these diagonals, you can see that biases that get locked in early in the forecast, they can persist throughout the forecast period. For instance, this one tends to be more strongly positive bias, compared to the surrounding forecast cycles, whereas this one's more negative. So things that happen early in the forecast can definitely have an impact later in the forecast. But then the largest thing that stands out here is the one I'm saving for last, and that is this large area of positive biases in the brightness temperatures up in this part of the diagram. Now, if you go to the bottom, you'll see that these are occurring between 4 UTC and 12 UTC. So this is nocturnal convection. And the fact that this is a positive bias is again indicating that there are not enough upper level clouds. And what was happening was that the convection was falling apart too rapidly across this part of the country during the night. And this is just a single case study, so it's hard to know if this is a more common pattern in the HRRR model. Okay, Greg shaking his head yes.
It is from the spring experimental project.
Okay.
CAPS. It's a very, very consistent feature.
Okay, and we're seeing this in the brightness temperatures too, where it's just.
And that's dwarf ensembles. That's not
okay.
Specifically.
Okay.
It's essentially the same basic configuration, more or less.
Okay. Okay, so to look at the evolution of the errors a little bit more closely, we decided to compute cumulative distribution functions for the 10.8 micron band. This is an animation that shows those distributions from forecast hour 0 to forecast hour 15. Now what we're looking at here are the observed distributions in the blue lines and the forecast distributions in the red lines. Each of the lines are for different forecast cycles within this 24-hour time period. So the first thing you can see is at the beginning of the animation, right here that the red lines are all lying below the blue lines for brightness temperatures between about, say, 245 and 280 Kelvin. And that's indicating that there are not enough mid and upper level clouds in the initialization, which again is consistent with what we saw a few slides ago. As we saw a few slides ago, though, that's then rapidly replaced by there being too many clouds in the upper troposphere, and that's indicated by these red lines lying above the blue lines by the time you get to like forecast hours 3 through 5. What's interesting, though, is you see that those red lines then slowly relax back towards the observed blue lines as you get into the later forecast hours. So again, this pattern is indicating that this is a model spin-up issue. There's not enough clouds initially. There are then too many, and then it slowly relaxes back to what was actually being observed. Okay, so in addition to the traditional grid point statistics, we also assess the forecast accuracy using the fraction skill score and the GOES brightness temperature data sets. Now, the fraction skill score is a neighborhood-based verification method that can be used to determine the spatial scales for which the forecasts have skill. This is typically taken to be a fraction skill score value greater than 0.5. Now, this slide shows a very simple graphical illustration of how the fraction skill score is computed. The first thing is that brightness temperature thresholds are chosen for the forecast and observed data sets, and are then used to mask a data sets in order to produce a binary yes/no data set that indicates whether or not a given grid point exceeded those threshold values. And then the fractions are computed for each grid point based on the surrounding grid points within different box widths, which can be as small as, say, like 3 grid points up to the whole model domain if you wanted to do that. And then those fractions are then aggregated over the chosen region before computing the fraction skill score. So here we're looking at the fraction skill scores for each of these 3 regions. Again, the top panel for the north central, and southeastern U.S. When we computed the fraction skill score, we decided to use the 10th percentile of the observed and forecast distributions. And this was done in order to account for a large bias in the forecast brightness temperatures, which I'm going to show later in this talk. Now, on the bottom panel here, this is a box plot diagram that shows the range of these fraction skill score values for each of these 3 regions. It's plotted as a function of the box width along the x-axis. It goes from 1 grid point, so basically typical grid point statistics on the left, to 101 grid points on the right. So that's a 300-kilometer box width as you get to the right side. So this was computed using all forecast hours and forecast cycles within this 24-hour time period. So if you go to the bottom panel then, you can see that the fraction skill score increases as you move towards the right, as you get to the larger box widths for all 3 regions. The highest forecast skill is in the north central U.S. In the red boxes. You get a little bit lower forecast skill in the southeastern U.S. with the blue boxes, and then the lowest skill was found for the central U.S. in the gray boxes. Now, the reason for the different skill in each of these 3 regions was really due to the different modes of convection. What this is showing you is that the more strongly forced and widespread convection up here in the north central U.S. Was simply easier to predict, whereas the more isolated convection across the central U.S. Was the most difficult to predict. Okay, so here we're looking at the evolution of the fraction skill score for each of these 3 regions. In this case, it's plotted as a function of forecast lead time. It goes from forecast hour 0 at the top of each panel to forecast hour 12 at the bottom. So this is the north central U.S., central, and then the southeastern U.S. at the bottom. The red colors indicate skill, and the blue colors indicate a lack of skill for that particular box width and forecast lead time. So I'm going to point out a couple things here. The first of these is that you can see that for all 3 of these regions, that the highest skill scores are actually found at the 1-hour forecast, not at the 0-hour analysis. And as we'll see later in this talk, the better skill at the 1-hour forecast was mostly due to a more accurate depiction of the cloud objects in the 1-hour analysis, and the 1-hour forecast when compared to the 0-hour analysis. Another thing I want to point out is that you can see at the forecast skill, not surprisingly, drops off as you get later in the forecast for all 3 of these regions, and that the the most rapid drop-off in the forecast skill is occurring for these smaller spatial scales on the left side of these images. This is basically just a measure of predictability. The smaller spatial scales are going to have lower predictability, and thus their skill scores are dropping off more rapidly. Okay, so now we're going to move on to the last part of this talk, where I'm going to be showing quite a few results from a more long-term seasonal analysis that we performed using object-based verification from MODE. And again, the focus of this was to look at the accuracy of the forecast cloud objects. Okay, so MODE is a forecast verification system that can be used to assess the forecast accuracy through a comparison of objects, whatever those objects may be. Now, we decided to focus on cloud objects occurring in the upper troposphere because that's what the satellite infrared brightness temperatures are going to be most sensitive to. It's a top-down, it's a downward-looking sensor, so we're going to see the upper-level clouds all the time. So that's what we're going to be focused on. With MODE, the first thing you need to do is to identify the cloud objects. And to do this, we used the 10th percentile, the brightness temperature distributions, which I'm going to talk about a little bit more detail in the next slide. Now, once you have those cloud objects, you then use MODE to compute an interest score, which is a measure of how well the forecast object matches up with the observed object. And to do this, you use different object attributes, some of which are listed here in the left column of this slide. Now, one of the strengths of MODE, or one of its weaknesses, depending upon your perspective, is that the user has to define the weights that are given to each of these object attributes. This can be very useful because it allows you to really focus on the kind of objects you're most interested in, but it does also lead you to the possibility of tuning it till you get the answer you want, which we, of course, try to avoid. So what we tried to do here was, we just focused on 6 different attributes, the ones that are listed here. We decided to give equal weight to the object distance and object size attributes because ideally, a forecast should contain an object of the correct size in the correct location at the correct time. It's hard to say which one of those is most useful, so we just gave them the same weight. So I'm going to briefly describe here the two the distance attributes up here, and then the area ratio attributes down there. Now, with the distance attributes, the centroid distance, it's a measure of the distance between the object's centers of mass. So if it's a circular object, it's going to be right in the middle. But if you have an object that has a different type of structure, it's going to account for where the biggest part of the object is at. So that's where the center of mass is going to be. And then the boundary distance is the minimum distance between the edges of those objects. We gave a little bit higher weight to the centroid distance because we care a little bit more about where the center of that object was actually located. And then the bottom 2 rows, the area ratio, what that is it's the ratio between the forecast object size and the observed object size. And then the intersection area ratio is a measure of how much they overlap. And we gave a little bit less weight to the intersection area ratio because we found that sometimes it can be artificially high when you have a small cloud object that gets fully enclosed within a larger cloud object. But nonetheless, if you add up the 2 weights up here and the 2 weights down there, you can see that we're given equal weight between the distance and area ratio attributes. Okay, so when we used MODE, we decided to use the 10th percentile of the brightness temperature distributions that were accumulated during the previous 10 days in order to define the edges of those cloud objects. Now, I do want to point out that this is not necessarily the edges of the cloud object. It is the edge of the objects that we're looking at. So these are the 10% of the coldest grid points that we are looking at with these objects. Now, the reason why we use the percentiles, as I mentioned previously, is because the forecast data tends to have a large bias in the brightness temperatures. And this can be seen in both of these panels. For example, if you look down here in the bottom panel, which is from forecast hour 3, the solid line is from the forecast. You can see that the brightness temperature in the 10th percentile is about 233 Kelvin. The observation is about 248 Kelvin. So that makes it very difficult to just pick a brightness temperature value. So that's why we decided to use percentile-based thresholds to identify these cloud objects. If you go up to forecast hour 0, though, you can see that, like with these red lines, that they are now reversed. So the dashed line's on the left, whereas it's on the right down here. So not only is there a large bias, but it's changing sign with time. So what we did then was, for the observed brightness temperature threshold, that's just simply based on all observations valid at the same time each day. Whereas for the forecast, or the simulated threshold, that uses data from the forecast from the same initialization hour and the same forecast hour in order to account for these tendencies in the bias. And the other thing I want to point out too is that the blue lines are from January of 2016. The red lines are from August of 2015. So we used mode for a 1 month time period for both of these examples. So far more than just the typical case studies that often get presented. Now in this case though, on the left here we have the forecast satellite imagery in the top and the third rows, and then the second and fourth rows show the mode identified cloud objects. And then on the right side we have the observed imagery and the observed cloud objects. The top two rows are from the August 2015 data, and then the bottom two are from January of 2016. So this is just a single time step within each of these month-long periods. Now the first thing I want to point out, like if you look at the top row, with the forecast imagery, you get these really dark gray and dark blue colors. These are very cold brightness temperatures in these thunderstorms. And you can see that they are quite a bit colder than over here in the observed imagery, which tend to be more like the lighter blue and the green colors. And the same thing occurs up here within the extratropical cyclone. They tend to be colder than what's actually observed. You can also see that down in the January data, where the cloud shield itself is a pretty decent size, correct location, but again the brightness temperatures are too cold. But when we look at the objects, by using those percentiles, you can see that we start to look at very similar types, very similar objects in both these cases. So by being able to use the percentiles, we really are able to lock in on the same type of cloud objects, in this case the ones in the upper troposphere. Okay, so the first thing we're going to do here is to look at the evolution of the number of cloud objects identified by mode. In this case, plotted as a function of time of day along the x-axis. It goes from 0 UTC on the left to 22 UTC over here on the right. This is a box plot diagram. So this shows the range of the number of cloud objects using all forecast hours and forecast cycles within each of these month-long periods. The red boxes are from the August 2015 data, and the blue boxes are from January 2016. Doesn't show up too well up here on the slide, up here on the screen, but the dark red and the dark blue boxes, which are like the second and fourth boxes in each of these sets, they're from the forecast, and then the light red and light blue are from the observations. So the first thing you can see here is that pretty much in all cases the red boxes are lying above the blue boxes, so that there are more cloud objects occurring during the summer than there are during the winter. Now because we're using the 10th percentile to identify these cloud objects, they should have the same total spatial area in both cases. So what this means is that the cloud objects are smaller during the summer than they are during the winter, and this is certainly consistent with the fact you're going to have more convective cloud features that are going to be smaller during the summer, whereas during the winter you're going to have many more large-scale synoptically driven cloud features. Now the last thing I want to point out here is, again, if you look at the August data in red, you can see this very distinct diurnal cycle, the number of objects. Maximizes here between 20 and 22 UTC, minimum here around 12 UTC. So again, this is consistent with a diurnal cycle in convection. Okay, so here we're looking at the number of cloud objects identified by mode, except this time we're plotting them as a function of forecast hour. So it goes from the initialization on the left to forecast hour 12 over here on the right. Again, August is in red and the January data is in blue. So the first thing you see here is with the August data that the number of forecast cloud objects in the initialization is much larger than what's actually being observed. So again, this is indicating that there are too many small cloud objects. Perhaps it's a situation where you might have a line of thunderstorms, for instance, that in the observations are one continuous object, but in the initialization are being viewed as discrete objects. You can see though that, excuse me.
Isn't it? I thought in the earlier slides what you showed is that there's not enough clouds at the initial time. So it's odd that it seems what you
No, it's actually consistent because part of not having enough clouds is instead of having these cloud features, like instead of having, say, like a thunderstorm with the more complete anvil structure around it, it might just be the thunderstorm core.
Yeah.
So
So radar data initialization.
Exactly.
versus satellite data initialization.
Exactly.
You're getting a lot of pinpointy things instead
Yep.
of broad things.
Exactly.
Got it.
Yep, so you end up with the warm bias
Yep.
and too many objects.
Yep. Perfect.
Yep. And then you can see by the time you get to forecast hour 1 that you have a pretty similar number of objects. And in fact, by the time you get to forecast hour 2, there aren't enough objects in the forecast data. And that then persists all the way through the end of this 12-hour forecast period. But one of the things that I find interesting about it is you can see that the largest separation between the observed and forecast number of objects is really between about forecast hours 3 and 5, and then those differences slowly decrease with time. So by the time you get to forecast hour 12, they're actually a pretty similar number of objects. And that's actually pretty consistent with what we saw previously in the talk, with the brightness temperature distributions, with the fraction skill score, things like that, where you end up having this probably the cloud field is probably least accurate a few hours into the forecast, and then it actually becomes a little bit more accurate again as you get later into the forecast. And again, this points to an issue with the model spin-up process. But then the last thing I want to point out, I don't want to leave the January data completely alone, so I'll focus on the blue boxes a little bit. You can see with the January data that the number of objects is quite similar initially between the forecast and observations, but then the separation becomes larger and larger as you get into the forecast period. In this case, you end up with a decrease in the forecast objects, which implies that there must be some kind of a merger of the objects going on. So you end up with a smaller number of larger cloud objects as you get deeper into the forecast period. No idea why. We haven't looked at that yet, but it's just kind of an interesting result. Okay, so now I'm going to spend a few minutes discussing performance diagrams. We decided to assess the forecast accuracy a little bit more closely using the cloud objects from mode using the performance diagram, which is a analysis method that combines 4 different verification metrics on one image. This includes the probability of detection, success ratio, critical success index, and bias. Now, to make this performance diagram, what we did was we took the mode identified cloud objects in the forecast data and also in the observations, and then we mapped that back to the HRRR model grid in order to have a binary data set of yes, no, whether or not it's in a cloud object or not, and then we could use those data sets to produce a yes-no contingency table, such as shown down here in the lower left. So a similar type thing like you would do with precipitation, for example. Now, the first metric that we compute with the performance diagram is the probability of detection, which is simply a measure of how many of the grid points in the observed cloud objects were also included within the forecast cloud objects. On a performance diagram that's plotted along the y-axis, it goes from 0 at the bottom to 1 at the top, with 1 being the best forecast. Then we also have the success ratio, which is equal to 1 minus the false alarm rate. And with the performance diagram that's plotted along the x-axis, it goes from 0 on the left to 1 on the right, and again, 1's the best forecast. Bless you. And the next up, we have the critical success index, or the CSI. That metric takes account of things like false alarms, misses when trying to determine which forecast is the best. And the CSI, with the performance diagram, is plotted along these curved lines that go from the upper left to the lower right. It goes from a value of 0 down here to a value of 1 in the upper right, 1 being a perfect forecast. And then finally, we have the bias. With the bias, that's plotted along the diagonal lines that don't show up too good here, but they emanate away from the lower left corner and then move up towards the upper right. The blue line shows the 1-to-1 line, in other words, no bias. So if you have data points that are over here, this indicates that there's an over forecast. Down here it's an under forecast. But for our case, because we use the 10th percentile to identify these objects, there shouldn't be much bias. It should be pretty close to that 1-to-1 line. Okay, so this slide, it shows the performance diagrams. This is for, both of these panels are actually the same, but what we're doing here is over here on the left, the colored boxes are from the August data, and over here, the colored boxes are the January data. So this allows us to more easily compare the results from both of these months. The different boxes are different forecast hours. It goes from forecast hour 0 down here in the brown and red boxes, transitions yellow, green, blue, purple, and eventually to gray for the forecast hours 11 and 12. So you can see that the forecast skill for each of these forecast hours, they're generally similar. They're all clustered in the middle of this diagram. But if you look at the critical success index, they do range from values of about 0.28 to a 0.48. So there definitely are some differences in forecast skill between these different forecast hours. If you look over here on the right, you can see that in most cases the January data in the colored boxes is farther to the upper right, indicating it has a higher forecast skill than what occurred during August. But if you go to the left, you see here, though, that the August data was actually most accurate at forecast hour, or the initialization of forecast hour 1. They actually had the best forecast accuracy. And what this is suggestive of is because of the strong reliance of the RAP and the HRRR on radar data, particularly like the thunderstorms, it seems to be doing a better job during the summer than it is during the winter. But because we're talking about convection, the forecast skill rapidly drops off with time. So it does pretty good forecast hour 1 and then ends up lagging what happens in January during the rest of the forecast hours. Okay, so now I'm going to spend a few minutes looking at a new metric that we are working on, that we developed, that we call the mode skill score. As was mentioned yesterday, we probably should not call it a skill score, so we'll probably change the name of it. But what we wanted to do with this metric was to try to combine just a tremendous amount of data that mode produces with each of these objects and try to combine them into a single value. Because mode, it provides information about each object, each pair of objects. So we're looking at a whole bunch of different attributes, object size, object location, and how do you make sense of all that data? It's very powerful because you have all that data, but at the same time, it'd still be nice to have perhaps a single value that tries to encapsulate all that information. So in the top row, you can see that the mode skill score, basically, it consists of two parts. We have a part here that is with the observed clusters, and then a part that's with the observed objects. I forgot to mention earlier that with mode, first you identify the objects, and then you can also choose to combine those objects into clusters if they're part of larger features. So that's what we did during this project. So we have to have two parts of this equation. So what we did was we made this an area-weighted metric. So you can see that both of these are divided by the total area. We did that because it's not really fair to give a small cloud object the same weight as a larger cloud object when trying to assess the forecast accuracy, because in most cases the larger cloud objects are simply more important. In the denominator, the total area that corresponds to the observed area of the cloud objects plus any unmatched object or any unmatched area from the forecast cloud objects. And then what we do then is we multiply the area of each of those observed objects or clusters by its interest value, which again is a measure of how well the forecast object matches to the observed object, and then we just simply sum it over all of the objects. So then the value ranges from 0 to 1. 0 indicates no skill, and 1 indicates perfect skill. So here we're looking at the evolution of the mode skill score applies a function of forecast hour, 0 on the left, 24 hours on the right. The red line is from August, blue line is from January. And you can see that the mode skill score values, they slowly decrease with time, simply indicating that the cloud objects are less skillful as you get deeper in the forecast. Not all that surprising. But again, you can see that the most accurate is happening at forecast hour 1, and it's happening for August in the red line, again between 0 and 2 hours. And again, this is very consistent with what we saw with the performance diagrams and pretty much all the results we've seen thus far. And here we're looking at the mode skill score plotted as a function of forecast initialization time. So this is the 0Z forecast over here, the 23Z initialization time over here. Now in this case, you can see it's pretty flat. There's really not much difference in the forecast skill depending upon when the model is actually initialized. This was a little bit surprising to us because they used new GFS analyses for boundary conditions at 10 and 22 UTC cycles. So we were hoping that maybe there'd be a little bit better forecast skill for those cycles because you have new information, but that's not what's actually happening here. It seems like it takes a little bit of time for that new information to get within the HRRR model domain. Okay, so we're almost done. Just got a few more slides here. I'm going to spend a few minutes trying to more closely assess why those 1 hour forecasts are more accurate than the 0 hour analyses. And we're going to do that using some of the object attributes that mode produces for these different objects. Now what we're looking at on this slide and also the next few slides are again these quilt diagrams. In this case what we're doing is we're showing the differences between the 1 hour forecast and the 0 hour analysis. Blue means that we have more objects in the 1 hour forecast, red meaning we have more in the 0 hour analysis. So along the y-axis is the object size. It goes from very small at the bottom to very large at the top. This is an exponential scale. Keep that in mind when we look at these slides. And then along the x-axis, we have the interest score for that particular attribute. So in this case, we're looking at the centroid distance, which again is the distance between the object's centers of mass. And we're going to start out by looking at the lower left corner. You can see that with the blue colors here, that the 1 hour forecast has more of these cloud objects with the very low interest values or interest scores. This actually indicates that the 1 hour forecast is less accurate. A little bit counterintuitive to what we were talking about previously. But the important thing to note here is that these are for the very small cloud objects down here at the bottom. So they're simply not going to have much of an impact on the overall forecast accuracy. So if we go to the upper right corner, you can see that the 1 hour forecast also has more cloud objects with higher interest scores, and these happen to be occurring for the large cloud objects. So it's doing a better job with the large cloud objects in the 1 hour forecast than it is in the 0 hour analysis. Now if we look at the boundary distance, which is the minimum distance between the edges of those objects, the blue colors over here on the left and the red colors on the right again show that the 1 hour forecast is less accurate. But again, it's for the small objects, so they're not having much of an impact on the overall forecast accuracy. Same thing happens with the intersection area ratio. 1 hour forecast is less accurate, but again for the small cloud objects. And then by the time we get to the area ratio, which is again the ratio of the observed object size to the forecast object size, you can see that in most cases, it's just noise here. There's not much difference between the 0 hour analysis and the 1 hour forecast, with the exception, with the exception up here in the upper right panel or the upper right corner. Again, the 1 hour forecast has more of the large cloud objects with higher interest scores. So if you look at these last few slides then, what these results are showing from mode is that the reason why the 1 hour forecast is more accurate than the 0 hour analysis is simply because the cloud objects are better. They have a more correct size and they're in a better location. So their centroid distance is more accurate and their overall size is more accurate. So this is kind of a novel use of mode, and this is a pretty useful way to try to better understand why those 1 hour forecasts are more accurate that you simply can't get with other verification methods. And that's it. Thank you for your attention.
All right, do we have any questions for Jason? We already had some good discussion, but if you have a few more out there.
So do you have some
We are recording this, so I'm going to ask you to use the mic.
So do you have some surface station to verify the result?
We could, but this is simply satellite-based. Well, every verification we're doing is satellite-based, so it's just a comparison of the observed and simulated
So
brightness
then,
temperatures.
how accurate is the satellite observations?
Well, okay, so the satellite observations should be pretty accurate. I'm going to guess, within 1 Kelvin. That's the sensor specification. So it should be pretty good. The forecast brightness temperatures, they have a large bias, and my very strong suspicion is that it's coming from the radiative transfer model that's used to produce those brightness temperatures. I really don't think that the HRRR model cloud field is that inaccurate. I really don't. I think it comes down to the cloud property lookup tables that the CRTM uses to produce those brightness temperatures. But for the purposes of our study, that bias doesn't matter because we kept focusing on those percentiles. So it's like we're still just looking at the 10% of the coldest clouds, regardless of what those brightness temperature values are. But what we're planning to do is the next couple months to try to fix that bias in the CRTM. We think we know where it's coming from, but now it's just a matter of getting it in there.
Other questions? No? All right, well, I'll just mention that Jason is here today and tomorrow, and then he heads back home. So if you would like to talk more with him, he's in FL3 1057, so please stop by. So, all right, thanks, Jason.
Thank you.